Hi students, I wanted to talk a little bit about this idea of heat and temperature and try and describe the difference between them. So you have behind me boiling one flask and one beaker. The beaker has about 100 milliliters of water and the flask has about 200 milliliters of water. So as you can see, they're both boiling. That means that their temperature is about the same. Now, when we talk about this idea of temperature, we're talking about this idea of a measurement of kinetic energy, how much the molecules within the system are moving. So these two are moving at the same rate at this point because I've put enough heat energy into both for them to be the same temperature. Does that mean that they have the same amount of heat? No, it does not. Because heat, the total amount of energy within the system, also depends upon the mass of the system. So twice as much water in one vessel would suggest that there is twice the amount of thermal energy in the larger vessel than there is in the smaller vessel. Now, when we talk about the kinetic energy, we're really talking about how quickly things move around. So let's just take a quick demonstration. I've got a little bit of this Congo red that I'm going to add to the beaker. I'm not going to put any, whoa, look at how quickly that moved. Now, maybe I should make that a little bit slower. The energy of the system is such that the coloring has immediately moved throughout the entire environment. That is a measure of the total kinetic energy, how quickly that newly introduced liquid was able to spread throughout the system. Now, they're both boiling, which means that if I were to measure the temperature right now for both of them, they should be close to 100 degrees Celsius. Now, I say close to because I don't know how accurate my thermometers are. But let's take a look right now at my two thermometers. I don't have a clue as to whether, yeah, okay, I can see that one's at 30. They are approximately reading identically. Might be hard for your screen to watch, but let's take a look. And if we were to get a close-up look, we would see that temperature has, man, this is really tough. The temperature has risen on my end. It says close to 100. Okay, so why is this one not at boiling? Well, because I've taken it off of the hot plate. Look, there's no more additional energy going in, and the liquid has stopped boiling, meaning, not that it's not hot, but that the kinetic energy is lower than the kinetic energy needed to change this liquid into a gas. So when I was adding energy, it was capable of transforming the liquid into a gas. You can see almost immediately the total amount of kinetic energy has decreased in both of these as we see that the temperature has stopped boiling. Now, what's going to happen to the actual temperature on these? Are they going to decrease at the same rate? Well, let's stick around to the end to see whether or not that's the case. But we should say that they're about the same, that one is about has twice as much water in there. And so because it has twice as much water, its heat capacity is about twice. Heat capacity is literally how much heat is it capable of holding. Think about the idea of someone who's really large and someone who's half their size. Approximately, the person, let's say one person who weighs 100 pounds and someone else who weighs 200 pounds, their capacity should be proportional to the increase. I'm not saying that the 200-pound person can literally lift twice as much as a 100-pound person. That would not be an accurate analogy, but the idea is that they should have greater capacity on average than someone who's smaller. Now, biology and people are much more complex than liquids. Liquids will behave the same in a precisely measurable fashion. This looks like it's 82 if we're looking at the water in the smaller beaker, whereas you can see it's even hotter to the touch. The one in the Erlenmeyer flask with 200 milliliters of water is still at about 90, meaning that there is greater total thermal energy in the Erlenmeyer flask than there is in the beaker. And as you notice, because the exit, the lip of the beaker versus the lip of the flask, the thermal energy is able to escape much faster in the one that is larger opening. I can hold this one without worrying too much about the total heat. This capacity of water to absorb and retain heat is an important part of the properties of water. So you ever notice that when you are, if it's August 1st and you are in Midtown Manhattan or in any major city, it is significantly hotter than if you were by a body of water. The reason for that is, let's say you're hanging out by a river. That river is able to absorb a significant amount of the heat that is being generated, that is from the sun, and it is able to absorb that. It has a high specific heat capacity. That high specific heat capacity allows for the sun's energy, the sun's thermal energy that is being generated, to be absorbed by the water. But what's happening in cities? Well, in cities, you will see that the metal and the glass and all that has a lower specific heat capacity. It is reflecting a lot more of that energy. So what happens is, let's say you're in Midtown Manhattan, or even worse, the subway. Well, all of that heat that's been absorbed by the metal is going to be reflected out. And so you're getting sort of a double whammy. You're getting the sun's heat, and you're getting more heat being reflected back at you from all of the buildings and all of the things that are around. Now, on the converse side, what winds up happening is the temperature difference between a city in the daytime and a city at night is significantly different, because while the sun's rays had already hit in the daytime and the building has been reflecting that heat, it's reflected most of the heat out during the daytime. So at night, the sun is no longer there, or is no longer visible, and so it is not directly heating up the surface of the city, and those buildings have already released a lot of their heat energy, which is why it could be 95 degrees, August 1st in New York City at 2 p.m., but give or take at 10 p.m. it could be 75 degrees. There can be a 20 degree difference, 15 degree difference between the daytime and nighttime. Now, conversely, inside of the buildings where the heat has been absorbed, that will release heat slower. So this leads to an interesting reality that it is much hotter at night inside most buildings than it is outside. And before the advent of air conditioning, what would be fairly common would be to see people spending a lot more time outside, and even sleeping outdoors. If you ever look at old pictures of tenement buildings and things like that, it would not be uncommon to see people sleeping on their fire escapes. The reason being that the outside of the building has reflected most of its heat, so it is significantly cooler outside of the building than it is inside of the building. So even with the windows open, it is still releasing heat more slowly. The materials, the wood and things like that, their specific heat capacity is different than the low heat capacity of the metal.